So let's talk about those three situations in terms of what's happening with the impulse and maybe what kind of physical objects are involved. So this is what I want us to think about. Let's see. I want us to think about, let's compare mass, velocity, and type of object involved in this short-term collision we're thinking of that produces this force curve. Okay? Type of object involved. So I just drew three different ones, I don't know. So if you get this kind of a force curve, what kind of things might be happening? Let's just make it easy. Let's just say we've got a ball and it's impacting a surface, all right? So let's think about what kinds of balls might be involved, and maybe how big are they, how fast are they going?
So like the first one could be like a soccer ball.
Okay, so yeah, let's just imagine this is a soccer ball.
Carry it for a longer time. And you are using a strong force, but not necessarily.
Okay, so if that's a soccer ball, the impulse, how long is it hitting the wall for?
On the wall? I was thinking like your foot.
Okay, so it's hitting your foot, that's fine.
Because then
You've got a fairly long contact time with that, right? Like a fairly big time interval. So this guy over here looks like, if you think about like the area under that curve, it's pretty similar to the first one, isn't it? Like I tried to draw it so it would have a fairly similar area. So its mass and velocity might be the same. What's different? The time interval. So if that was a soccer ball, what might this be?
Baseball.
Tennis ball. It's a golf ball.
Let's just go with golf balls or something better.
It's bowling ball.
It'd be golf, I think.
I think that you guys are on it. What's the main difference?
Bowling
the
ball.
weight.
I think the weight. Let's imagine this is a bowling ball that's equivalent weight, like it's a real light bowling ball. The difference is the time, and why is that different if you compare like a soccer ball to an equivalently weighted bowling ball?
Soccer ball's
Easier to
a
get
short
faster.
ball.
The soccer ball deforms, right? It like smashes against your foot when you kick it.
And then
Whereas if you kick a bowling ball, is it gonna like smash against your foot? Not really, it's just gonna like bounce off. Yeah, your foot's gonna be painful. That's why I was thinking of like using, just you think about dropping a soccer ball. If you drop it on the ground, it's gonna deform and stay contacting the ground for a longer time period, giving you that longer delta t. If you drop a bowling ball on the ground, it's gonna like bounce immediately, right? So that time interval is going to be a lot less. So then what might this be if we're thinking about dropping something else, another kind of ball?
Tennis ball.
No, soccer and tennis gonna have
I think maybe a tennis ball. It's kind of got a time interval that's in between those two. I agree, that might be it. And what else would be true about a tennis ball? It's going to have less mass velocity. Remember, you're thinking about when you take force times time, you get momentum. If you drop a tennis ball, it's going to have a lot less momentum when it impacts versus a versus a soccer ball or versus a bowling ball, even if it's a light bowling ball. Does that kind of make sense? That's why there's less area under this than there was under either one of those other ones. Does that make sense? Okay. So that's what we're talking about an impulse. Let's look at that problem that I gave up on yesterday. So I had a headache or whatever.
Let's forget about it.
Yes, I agree. Embarrassing. Okay. So let's look at that one. You might want to open up your book for a second. Can somebody read me example 7.6? So I think we're supposed to consider like a person jumping down a certain height. In fact, I think I know it now since I looked it up this morning to make sure. So I think we're given that a person of mass 70 kilograms, how far down did they jump? 3 meters. That's like jumping off the roof, isn't it? So the change in height is like 3 meters. So they ask us to figure out the impulse that's created by that impact, right? So like the impulse of when they're like hitting the ground. That's the key, like just that little time interval right when they hit the ground, that impulse, okay? So we're supposed to figure out that, and then we're supposed to use that to figure out how much force the ground is exerting on them if they land like this versus if they land like you should and go like that, right? So what's the difference in those forces? What do you guys think? Like when they land stiff leg, how much force is it going to be? A lot. And when they bend their legs and that impulse is directed over a longer time period, the force is going to be less, which is going to be good for things like their bones. Okay?
Is it really a different force though? Or
Yeah.
is it the same force? and
It's
just
the same
like
force
more
over a
weight?
longer period.
It's not the same impulse which changes the force. Because remember, impulse is force over delta t. So watch. Good question, good question. So let's see. A, we've got impulse. We need to figure out that. That's force, average force over a time period. Okay. Part B, I said, what's the stiff leg force and what's the bent in part C? Okay? So first, we need to do the impulse part. So A. So we're going to say, okay, impulse equals change in momentum. And how can we do change in momentum? That's really just because the mass isn't changing, right? It's mass times change in velocity. So this is going to be mass times final velocity minus initial velocity. So we just really need those velocities. Now, did they give us those in the problem? They didn't say anything about how fast anything was moving. We have height, we have gravity, we can use kinematics. So we say, okay, let's just go over here and do a little thing and say, all right, final velocity squared is initial velocity squared plus, what is it? Help me out.
2a delta.
2a change in height. There we go. This marker is done.
Nailed it.
Yes, on it today. Okay. So what do we got here? What do we know? So if we're thinking about, I guess we could draw a little picture over here. So here's like the top of the roof. Here's the person falling. And then here's the ground. So right before we get to the ground, we're looking for that, aren't we? Like how fast are we going? And I'm picturing it slightly above, like right before, okay? So the initial velocity is going to be what? 0. We want the final velocity, and we know gravity is 9.8, and the change in height is 3. So can't we just go root 2 9.8 times 3 and find that velocity? What is it? 7.7? There we go. So that's the velocity right here, right before we hit the ground. But remember, when we're doing the impulse, what place are we talking about? This is a little bit sneaky part. We want to think about the impulse generated just right there. So is that the thing we want to put in for the final velocity? For that impulse little time period?
Well, the final velocity is 0.
Yeah, like when you actually hit the ground, you're going to be going what? 0. So the final velocity we want to consider here is 0. We really want this guy to be the initial. And we figured it was 7.7. Does that make sense? Okay. So we've got the mass is 70. Then we said the final is 0 minus 7.7. And we can get the impulse. Okay? So this is the impulse. What is it?
Negative 540 meters.
It's about, right? Why is that negative? Because the ground's generating that impulse, right? What's up, Mr. Jordan? Okay. Okay, so now what else do we need to do? We need to calculate the stiffness here, right? So let's see. So we've got that. Let's do part B. So the stiffness. What else did they give us? They gave us more information. We were also given that
The embodiment was 1 centimeter.
When we're stiff-legged, the body only moves a little tiny amount. So body only moves 1 centimeter for stiff-legged, okay, during impact. So here's what we're going to do. We're going to calculate the average velocity. So it's an average, so I'm going to divide by 2. So initial velocity, final velocity. Okay, so we'll do that. Then we're going to use that with distance equals rate times time. Why am I doing that? I'm going to write this as time that way. Okay. Let's get those. So what have we got for our initial and final velocity for just that little impulse period? We've got 7.7, 0, so that's going to be 3.85, okay. Let's round it, let's go 3.9. Same significant figures. Here we're going to put in, what, 1? 3.9 delta t. So this little time interval that we're considering for our impulse is going to be...
Shouldn't you convert that to meters still?
Oh yes, that's right. This is in what? So I need to put what here? Times 10 to the... There we go. Or 0.01, right? Either way. So what is that? What is it? I think it's this. Only reason I want you guys to do it is so you believe me. Okay? So that's 2.6 times 10 to the negative third seconds. A very small amount of time, right? That makes sense. We're considering a very small time interval. So now we can use average force times that equals... This is impulse, right? We just figured out the time period of that impulse. What else do we already know? We know the size of that impulse, don't we? We used the momentum part. We used momentum to calculate the size of that impulse. So this is equal to, I really just want the magnitude. I'm not going to use the negative part. I just want how big is it, right? The impulse was 540 newtons. We just calculated how long it took for that little impulse, which is this many seconds. So I'm going to put that many seconds in. And now I can calculate the average force. And that's what we're trying to do, right? How much force is generated when you land stiffly like that. So the key here is that we used change in momentum version of impulse to get the size of the impulse. Then we used just some pretty basic stuff to figure out how long that impulse took between here and here, just this little tiny guy, and then we can just get the force. So the average force, I'm going to call this stiff. It's going to be what? 540 divided by that?
2.1 times 10 to the fifth.
Yeah. Now let's talk about units just for a second. Paul brought that up yesterday. Impulse has units what? Force has units newtons. Time has units seconds. So when you look here and you go newtons times seconds, what's this unit down here? You get a force, right? So this makes sense because this is in newtons. You can see it right there. So there's nothing funny going on here. It's just that. Okay, so there's one little thing we were talking that we kind of forgot about. Let's talk about the free body diagram of a person at some point. So this is like the force. There's really two forces going on here, aren't there? There is, what's this guy? Gravity. And this guy is like the ground pushing up. So really, don't we have to think about both of those things? So here's what I said. I said we're trying to really figure out the force exerted by the ground. So the force exerted by the ground is going to be minus that, right? Force exerted on the ground minus the force of gravity is going to be this stiff force that we had. Does that make sense? Like the force that we get in this impact because of the impulse, we calculated it. That's the force due to this impulse from that collision. Okay? So it's got to be equal to, you've got to think about the free body diagram. So you've got the force of gravity and the force the ground is pushing up on you. What did they really ask for? I'll go back and look at it. They didn't ask for like the force generated in this situation. They asked for the, look. They didn't just ask for the force generated. They asked for the force exerted by the ground. So really you have to think about that like this. So what is mg? It's going to be 70 times 9.8. We have this is 2.1. So the force they really asked for was this force on the ground. I think you'll find when you add that to the other side, when you go 70 times 9.8 plus that force we just calculated, what's that equal to? I don't think it makes much difference. In other words, the impulse, I mean, the force due to the impulse isn't affected very much by gravity. Gravity's not really doing too much right there.
0.4 times
Teachers, at this
10
time, would you please
8.
release the boys soccer team? Thank you.
I don't know about that.
Oh wait, we're adding.
You're adding, right? You're just adding that. This is going to be pretty small compared to the force that we just calculated.
Yeah.
So it's what, 210? 686.
So you wouldn't even
Significant
see it with
figures, it's like
6.
2.1 times 10 to the fifth. Did you even see it when you did your newtons? I mean, when you did your significant figures?
No.
It really didn't make much difference, did it? So that's a lot of force though, isn't it? That's like a huge amount of force. So let's do part C. So part C, I'm going to leave this part up here. Part C is the exact same thing, except they say change the amount you move from that to what? You guys all tape this, so make sure you watch it this weekend.
Alright,
okay?
thank you. And then we have other videos to watch, right? Like,
There's like one or two. There's one 2-minute one and one 10-minute one from the Olympics.
There's other videos too, right?
Yes, there are.
So the legs are bent. When the legs are bent, so.
Okay, you guys.
Oh.
So, when the legs are bent, instead of just moving 1 centimeter, you move a lot more, right? How much did they say? That makes sense. A lot more movement. So I think we're just going to do the same calculation again for that, and we'll see what the force is. Hopefully it's a lot less so that we don't break our legs. Okay, so this time, that's going to stay the same, isn't it?
So yes.
Is the velocity impacted, you guys?
Sorry.
Okay. The only thing that's impacted is this, right? So you're going to go 0.5 meters equals that same velocity. So this impulse is going to take a lot longer time, right? It's going to take 0.5 divided by 3.9, which is what?
0.128.
0.128. So we'll go 0.1.
3.
Yeah, 0.13 seconds. Before it was like 0.00, much smaller time interval, right? So that's going to help us a lot when we look at the forces involved. So now we're going to say, okay, what's next? Somebody help me. Same calculation.
Average force times change in time.
Average force times change in time equals? Equals momentum, I agree, but what do we figure it out? What was the change in momentum?
Yeah.
540, and we said the change in time is, the time this takes is, so this guy, and let's call this average force instead of stiff, let's call it bent. think that's going to be a lot less force, isn't it? Maybe. Still a lot, but I mean, even if you jump off the roof and bend your leg, that's still a lot of force, but less. What is this? 1.2 times 10 to the third. Okay, that's 2 orders of magnitude lower, right? We had 10 to the 5th before. And what are we going to have to do? Think about gravity again. Remember, that's just the force we're thinking about with our impulse. We've got to add gravity. So we go plus. So the force that's exerted by the ground is that plus mg. But once again, is it really going to make an impact? Let's see.
Probably still gonna be 4.
It's probably still going to be the same, but let's check. Let's check. I got a little bit this time. Remember, when you're adding 70 times 9.8 to something smaller, it's probably going to have more of an impact, isn't it? So what do you get? You get 4886. So that's about 4.9 times 10 to the third newtons. So I made a little bit of an impact on that one. So another thing we could do is actually later in this book, right before Christmas break, we're going to do a little bit of statics, and it actually talks about like the ultimate strength of materials like steel and anything else, spandex, and also bone. In our book in chapter 9, there's this thing about the ultimate strength of bone. Should we go look at that or not? Should we go look? Let's go look. Look at chapter 9. Let's see if this force, so we got 2 forces here, right? We've got this force right there, and then we've got this force right here for the bent legs. Let's see if that's enough to break your leg. So is this right here, when your legs are stiff, enough to break your leg? Let's see if we can calculate that. So I think it's on, what did I say, page 241? 241. So on page 241, I think there's a table that has the ultimate strength of materials listed. Does it have bone?
Yep.
What's it say the ultimate strength of bone is? Shear strength is like sideways stuff. We'll talk about shear later.
Tension strength.
Compressive strength. Wouldn't this be compressive? Yeah.
170 times 10 to the 6th.
So it says 170 times 10 to the 6th. What are the units it gives there? Gotta watch your units.
Mass squared.
Newton,
Sure.
Newton meters or Newton meters squared? Newton meters squared. Okay, so that's not newtons, right? So we need to like compare to newtons or something here, right? What was the force we had before for the stiff? The force stiff? The ground exerting in that case? It was 4.1 times.
Wait.
That was the force bend.
Stiff or
That was the force bend.
The force-
And it was times 5.
Force ground stiff.
5.
Okay.
Times 10 to the 5th.
Was it 5?
Yeah, that's what I got. That's how we said that.
That's right. That's what I was remembering. Okay. That's in newtons, right? That's a force. Is this a force? No, it is not. It is some measure. We need to like equate it. So if we were going to equate this, this is like compressive strength. It's force per. And what is meters squared?
acceleration.
That's meters per second squared. This is an area. This is force over an area. Doesn't that make sense if you're thinking about compression? The force is going to be exerted over some area. So let's think about a person. How much area do you think their 2 feet take when they hit the ground?
1 square foot.
1 square foot? Do you want to estimate it as that and convert it? And let's think. So 1 square foot.
Would be like a third of it.
So let's convert that. So 1 foot squared, we needed to change it into meters squared. Help me out. Look it up.
1 meter equals 3.281.
So 1 meter is 3.828.
28.
Let's go for that. Is that all I have to do?
Square.
I need to square it, right? So what am I going to do with that? So that's how you convert feet squared to meters squared. So what should I do with that? Take this guy. So this is Newton. So if we just had 1 foot squared, you guys decided just 1 is about how much your feet take. So this would be like feet squared. What do we need to do with that?
Multiply it by 1 over whatever.
Let's make sure. Okay. So if we have that per foot squared.
Wouldn't you just divide by 3.28 squared?
Yeah. I think so.
Because that's your foot squared.
But it's Newton over foot square. It's not.
Oh, is this at the bottom?
Yeah.
Oh, I was like, what is going on here?
Yeah.
That makes a lot more sense. Okay. So what do we need to do here then? We need to put this down there, right? So now what do we need to do to fix this? I think we need to multiply this by 3.28 squared. There we go. What is that? Because that's on the bottom. If you want to do it like this, here, I'll convert it for you. Here we go.
Divide by 1 over
Feet squared,
Yeah.
meters squared, 3.28 squared goes there, does it not? Yay, Newton meters squared. So what do you get when you multiply that?
2.3 times 10 to the 6.
Is your leg gonna break?
there. No.
You got
It could happen, right? But look how close it is.
That's 2.3 and 170.
Yeah, but
That's like 2. That's like 2. Because if you write that in 1.7 times 10 to the 8.
2 orders of magnitude difference. Yeah, maybe your leg is safe on this one.
But if there's any shear force, then.
Sure, we said we
There's some other factors here. I don't know. That's kind of cutting it close. The other way, is your leg very likely to break the other way?
Yeah.
It's going to be a whole lot when you bend your legs.
Oh.
I'm just saying in that case it wasn't 2.5, it was like times 10 to the third. This thing would be way less than the threshold value, so you'd be definitely safe. You should be fine unless something weird happens. You hit like a rock or something. Okay, let's talk about another example. That was cool. Good unit stuff. I'm glad we went over that. Let's see. What else we got? Let's look at 7.7.
you taught here.
Oh, I need a couple definitions first, a couple more definitions. Let's get these down. Sorry, it's going to be a long day. So, we need to talk about 2 types of collision. I don't know if we'll get to them both. You might have to watch one over the weekend. But a collision
Should I change?
where kinetic energy
Did you work it?
is conserved.
What were you at?
If kinetic energy doesn't change before and after in a collision, we call that elastic. So that's when, like, yeah, those. But we're not thinking a collision there, right? It's called an elastic collision. So we're going to look at some examples here in a bit. So that's what I'm talking about there. Another definition that we need, leave a little bit of space, is an inelastic collision. So let me get that down. So an inelastic collision, there's some kinetic energy lost. That kinetic energy probably goes into what? Heat. Possibly with like nuclear particles and stuff, it could go into other forms as well though. Heat or other energy. Brenna, what did you need? It'll be a bit. So this kind of thing, you might imagine, is very hard objects. So for instance, if you have 2 pool balls and you knock them together like when you're playing billiards, that's a very elastic collision. It's not perfectly elastic. No collision is really perfectly elastic, but that's pretty elastic, okay? The softer the balls would be, the more inelastic your collision would become. We're going to watch a video by the end of class that kind of shows that a little bit better. Okay, so one thing, a couple other things. We're going to mainly look at elastic types of collisions because they're a little easier. The more inelastic a collision is, the harder to describe it is, so we're going to kind of stay away from that mainly. Okay, so this elastic type of collisions are common in the microscopic world. So later this year when we talk about electrons and protons and atoms interacting with each other, a lot of the time if they have any kind of collision, you're going to consider that as pretty much elastic. They pretty much bounce off each other perfectly. Okay? And then like I said, billiard balls are a good way to think about this. So those are a good approximation. Anything that's squishy, you can't do this way. So there's one little formula. I'm not going to go into the derivation. We just don't have enough time. So there's one little thing. If you have an elastic collision, here's a nice thing you know. The velocity of the things that are impacting, so thing A and thing B, there's this little equation they follow before the collision and after the collision. So those little primes do not mean derivative if you're in calculus. Those little primes mean after. In physics, if anything ever has a prime in it, you could probably bet it means not before, but after. I don't know, it's just another notation they use. So this, if we have an elastic collision between objects, we can use this little thing to help us. And we'll see where we need that right away. We're going to use that in 2 examples, and we'll be done. Okay. Okay, so the first one we're going to do is 7, 7. And this one just has billiard balls, okay? So we'll do one with billiard balls and we'll do one with some subatomic particles. So that's what we'll do. Let's look at 7, 7. I don't even have my book on me. Can somebody read it?
Billiard ball A of mass M moving with speed v collides head-on with ball B of equal mass at rest. What are the speeds of the 2 balls after the collision, assuming it is elastic?
Okay, so we want to find the speeds of each ball after the collision. They gave us some information about before the collision. So let's see. Okay, so we've got 2 equations here. One, we're going to apply conservation of momentum. So equation 1 is that mass times velocity equals that. Okay?
It's not given in the book though.
So it says that in the book. Why am I saying that's true? So that just comes from conservation of momentum. The momentum before equals the momentum after.
Because no energy loss?
That's just it's not the conservation of energy. Momentum is always conserved too. Remember how I talked about charge as a conserved quantity, energy as a conserved quantity before and after in a closed system, and momentum is also conserved in a closed system. And this is a closed system. We're not pretending there's any other things interacting with our 2 billiard balls. So we've just got 2 billiard balls.
No friction, no thermal, no nothing.
We're imagining this is perfectly elastic, so we don't have to worry about that. Okay.
If things were perfect.
So the 2 billiard balls, they said what happens? I forget. Billiard ball A of mass M is moving.
Excuse me, Mr. McGee?
Yes.
Need Jessica Marie for the sign out.
Okay.
Thank you.
Are you taping this?
Yeah.
Okay.
So, but ball B is at rest. Is that it? So this guy has velocity 0. This guy has a velocity at the beginning. And then we're trying to figure out how fast A is going after and how fast B is going after. So those are the things we're trying to figure out. Okay? So this is the first thing we can do. That just came from conservation of momentum. momentum is the same before and after. Okay, we don't know any of these quantities yet, but what's nice about M?
Stays the same.
It cancels out, so we get this. So there's one thing we know. Now I said we're considering it perfectly elastic, so we can also apply that other thing I showed you. What was that other thing I showed you? We had another equation we just learned. What was it? Help me out. Just for elastic circumstances. B prime minus VA prime. Now, do we know any of those things? I think we do.
Zero.
Which one's 0? This one goes to 0, right? So we know that VA is this plus U.
That's like
Do we know anything else? I don't think so. Okay, so we have in these two equations, remember up here I was just that this is really VA. So that's really VA, should have put VA, my bad. So we have VA in both, we have VA prime in both, we have VB prime in both. This is a system of two equations, two unknowns. We could use substitution, we could use elimination. Looks pretty close to eliminatable, doesn't it? Right now, if you just line them up, So I'm gonna go VA equals, then I'm gonna line them up. So I'll write this one down, and then I'll write this one down. So I've got a negative VA prime plus VB prime. When you add those together and eliminate, you get 2VA equals 2VB. So we've got that, and now we can do what? The 2's canceled. Yeah. So VA equals VB prime. Okay.
So that means that VA is possibly going to end up being 0 because it's transferring all its energy into VB. Because the beginning velocity of VA is the same as VB afterwards. So it's inverted.
So what's really happening in my picture over here?
All of the momentum is
Here's A,
transferred.
here's B afterwards.
A is now stopped and B is now potentially.
So this guy is now 0, and this guy now has velocity.
A.
Same thing as that. I should really draw them the same size, shouldn't I? It's not really all going off to the side, but same size vector. How would you know that from the equations? You could take this and plug it back in. Either one, just like in substitution, and you're going to get the other thing equals 0. Okay, does that make sense? Like in pool, isn't that what happens? When you hit two balls, like if one's standing still and you hit one, this one then stands still, and the other one flies off with about the same velocity. It's about the same velocity because this really isn't perfectly,
There's friction.
because there really is friction. It's not perfectly
So
elastic.
so it's felt like friction equals 0.0.
Yeah, you lose, well, the felt would also have an impact, you're right. But also, even when they do collide, it's not perfect still. But we're just kind of in a perfect world. Okay?
So can you plug it back in like this?
Yeah, let's plug it back in. So, where should I put it? I should put it
Put it in that one, the first one.
VB prime equals VA prime plus VB prime. So subtract the other side.
Oh, okay. That was simple.
There you go. No, it's good to do that though. Okay, last example for today. Let's do another elasticy type of collision. Okay? So you're mainly going to just have elastic collisions, no inelastic ones. It's too hard for now. Too hard for this year. See, Jessica. Okay, let's look at 7-8. Read 7-8 real quick. I'll give you a second. Okay, do we have a grip on what's going on? So we've got what happening? Let's list our givens.
Proton
So we've got a proton, little guy.
and a helium.
He's moving, right? He blasts inside here. I don't know if someone's firing a proton gun or something. So here's like an atom. He's not just hitting the atom because an atom really isn't completely solid, right? It's like a cloud. There's electrons moving around in that cloud. What does he impact?
The nucleus.
He impacts the nucleus.
Positivity.
Atom.
We haven't learned a whole bunch about what it's made of. Does it say what it's made of? It says it's the helium nucleus. It doesn't say what it's made of, right? What is in a helium nucleus? Does anybody know?
Yeah.
Helium is 2. That means it has 2 protons and it also has 2 neutrons. Electrons, I don't know, maybe 2 electrons? I don't know. We'll learn about this by the end of the year a little bit more firmly. But anyway, it's passing through those electrons and just hitting the nucleus, just hitting the protons and neutrons, that little package in the middle. And it says what else about the situation? We know that the mass of this guy is 1.01 U. U is just a new unit. It's just, it doesn't say how many kilograms it is there?
1 U.
Is it a lot of kilograms? No, it's really small. Does that make sense? Yes, it's a proton. It's microscopic, so we're good. But maybe we don't even need that. So we'll just say that's the mass there, mass of the proton. Mass of the nucleus, they say, is 4.00 U. Okay, so let's apply what we know, conservation of momentum-wise. Okay, so what's one equation we can get? Just conservation of momentum. So does it give us a velocity? It doesn't. It had to give us something,
Yeah.
right? Which one? This guy's stationary, right? So we know that too. This guy's velocity, velocity of the nucleus. I'm going to say velocity of the helium is 0. Velocity of the proton is
3.60 times 10 to the 4th meters per second.
Take a chance. Okay. So first we're just going to apply conservation of energy is not the only thing that's conserved. In this chapter you have momentum that's conserved. So momentum of the two things, mv before and mv after. So now we got to subscript those guys. This is going to be the proton. So proton, helium, proton, helium. What should I really put on these things? So that we're talking about afterwards, but that's just conservation of momentum. Okay? So now can we come up with something else? We've got that other thing for elastic collisions. Let's see, can we simplify that down at all?
Second term is 0.
That goes to 0, that's nice. So we have MP, VP, and we know some of the masses. We could start sticking those in, but what do we not know? We only know this velocity. What do we know over here? We know that, we know that. Do we know either one of these? So how many unknowns do we have? 2. So if you have 2 unknowns, how many equations do you need to find them? 2. 2 unknowns means I need 2 equations. We've only got 1, so let's go and see if we can search for that other equation. We're gonna have a system again. Does that make sense? So what other equation do we have?
That one.
The one I told you for elastic, which is what? Help me with the subscripts. VP minus
V
velocity of the helium. Good.
equals VHE prime
Good.
minus VP prime.
Good. So we've also got that's true for an elastic collision. So how can we take this and maybe combine it with that? I don't think it's too bad. I mean, I don't want to make it messy, but let's see. Can't we just like substitute maybe? I think we could just substitute. Can't we just solve for VP and then put it in right here? Which one of these is 0 again? So we know that's gone. Let's make that a little easier. So we've got VP equals So I think it's up to you. You can stick stuff in where you want it. Let me see what I did, just so we don't go down the rabbit's hole. I don't know. I just want to try it. Let's see how it goes. So we can put this right here, right? Okay, try that. Is that a good choice? What are our two unknowns again?
The velocities.
Which velocities?
Primes.
Do we know this one?
Yes.
Do we know this one?
No.
So this is unknown, and this is
I don't know.
unknown. So was my choice good? I don't think there was anything wrong with my choice, but was it good?
They're both in there.
Now you've got an equation with two unknowns still. Does that help? No. So I'm glad I actually made that decision because it was a poor one. What should I have done instead? This is just a number. Don't we know this? In fact, if you're uncomfortable, could you put in that number right now? Yeah, you could. Maybe we should, just so we're feeling a little bit better. Put in 3.6 times 10 to the 4th. And then you'll see why better solve for one of those other things, hadn't I? So let's see what we're going to have over here. Maybe we should solve for VP prime, for instance. So if we solve for, I'm going to solve for the helium. So if we solve for the helium velocity afterwards, it's going to be that 3.6 number plus that, right? So now we can take this and stick it right there. Okay, so VP prime plus M helium, and now we can put 3.6 times 10 to the 4th plus VP prime. It's just ugly looking stuff. Don't let it really flip you out. Once again, what's this over here? It's just a number. You know the mass of that, you know the mass, you know the velocity there, so don't let it freak you out. So how many unknowns do I have in here? I've just got one. It's right here. So what do I have to do to get it? I need to like move stuff away from it. So you've got like, see, I'm gonna see that number. It just makes it ugly. That's just VP, right? So what do we have here? We have MP V prime P plus the mass of the helium times the velocity plus the mass of the helium times the velocity prime. This guy can go over here. So I'm going to have the mass of that, velocity of that, minus the mass of that, velocity of that. Got rid of that part. Factor this guy out. Divide it. Finally, we have one of them. So we can plug in those numbers now. So let's see. So we're going to have 1.01 times, yuck. See, I should have followed my notes. That way we didn't get stuck with this. So anyway, I'm not going to stick all the numbers in. You get the velocity is this, or that one. Once you stick them all in. Okay? And then if you wanted the mass, the velocity of the helium, should be easy now. You could use that right there. So you just say that plus that. You have the velocity of the helium. Okay? Don't let this freak you out. It's just a very easy system of equations. The only thing that's hard about it is what?
Notation.
The notation. Like the symbols get sticky. So if you want to make the notation simpler for yourself, as long as you keep track of mass of one thing, velocity of the other thing, and you keep track of what's unknown and what's not, you'll be fine. So, okay? So notation is kind of yucky. But... Alright, so that's all I wanted to do today, except let's maybe watch one of those videos. So for you viewing at home, now you want to watch the 2 videos on Chapter 7. And make sure you also watch the baseball one, if you haven't already.